Good morning, everybody. So today is going to be a lab session. So you should have your own laptop. And we're going to start with the notebooks that we started last time, which is this differential drive obstacle avoidance notebook, which you can find inside the optimal control /Kazadi folder. So last time we saw how we can use optimal control to find optimal trajectories to drive a differential drive robot, so a unicycle, to reach a target while avoiding a circular obstacle. That was the easiest kind of obstacle we could imagine because, well, the collision avoidance constraints is a very simple quadratic form. So it's very easy to formulate, even though we saw that there are better ways to formulate it than others. So for instance, using the square root, we saw that could lead to troubles because the square root of 0 is not defined. And so it's better to formulate it without the square root. And we also saw that even though the trajectory is collision-free, it's actually collision-free only at discrete time steps. But if you check the position of the robot in between time steps, then actually you could have collisions. And the last thing that we discussed was how to ensure also collision-free trajectories in between time steps. The next topic I want to discuss is what if the obstacles do not have a circular shape? Because having only circular obstacle is quite limited. So another class of shapes that is actually much more general is polygons. So if we have obstacles that have a polygonal shape, and I mean any polygonal shape, as long as it's convex, how can we deal with that inside the trajectory optimization problem? So let's first define what we mean by a convex polygon. Well, we're going to define a convex polygon by the list of its vertices. So since we are working with a differential drive robot, here everything is in 2D. But actually everything I'm going to tell you here can also be extended very easily to 3D. You just use three-dimensional vertices for the polygon. And then the polygon is defined as the convex hull of its vertices. So any convex combination of the vertices represents a point that belongs to the polygon. So if we want to check whether a given point P is inside the polygon, so is in collision with the polygon, I think the most straightforward way to do so would be to use this convex hull definition. So we can try to express the point P as a convex combination of the vertices of the polygon. So we try to find these values lambda i's, where we have one of these values for each vertex of the polygon. The lambda i's should all be between 0 and 1. Well, it doesn't say it should be between 0 and 1, but if they should all be positive, well, not negative, and the summation should be 1, of course, none of them can be greater than 1. And this gives us a convex combination of the vertices. And if such a value of lambda exists, then we know that P belongs to the polygon. If instead it doesn't exist, then we know that P is outside the polygon. So that's one possible way of checking whether a point is inside the polygon or not. Is this a good way for us to do trajectory optimization?
It requires a big computational time, so because they are this type of devices.
It's not too complex. I mean, it's a simple problem we have, I mean, this is a linear constraint. This is a linear constraint. This is a linear constraint. They're all linear. So computation time is not an issue here. There is another issue with this approach. So suppose that the point P, which would be the robot in a trajectory optimization problem, is not in collision with the polygon, which is actually what we want. What is the value of lambda that the solver finds? We are sleepy this morning, eh? It seems you're completely lost. Then ask me question, otherwise I don't know how to help you.
Zero.
No, it's not zero. Zero wouldn't satisfy this constraint here. Summation of lambdas should be equal to 1. So you cannot have lambda equal to 0. Let me ask a simpler question. Suppose that the robot is exactly on top of the first vertex of the polygon. What is the value of lambda?
All zero and one is one.
Yeah, the first lambda is going to be 1, and all the other lambdas are going to be 0. If it's on the second vertex, we're going to have 0, 1, 0, 0, 0, 0, 0, 0, and so on and so forth. Okay, so that's a case in which there is collision, because the robot is on or in the polygon. What if there is no collision?
The
Take your time.
meaning the vertex with the smallest distance from the node is zero, and then the other A is one, and then the others are zero.
Well, but if the point we are checking is outside the polygon, then there is no solution. I mean, it's written here. If a solution does not exist, then it means that P does not collide with the polygon. So to verify that there is no collision, the problem must be unfeasible. So is this a good strategy for our trajectory optimization problem? No, of course not. Because we need an unfeasible problem to check that we are not in collision. We have a feasible problem only if there is collision. So this is not a good strategy. So it's fine if you just want to do collision checking, then you can use this. But if you want to optimize collision-free trajectories, then this is not a good way to check collision. So we need to figure something out. So a better strategy is the following one. If we have a point and a set of vertices defining a convex polygon, and we want to check if they're not in collision, so the point does not belong to the polygon, a possible strategy to do that is to try to find a line that separates the polygon, so the vertices, and the point. What does it mean? That it separates the polygon and the point. It means that the point is on one side of the line, while the vertices of the polygons, they're all on the other side of the line. If we can find such a separating line, separating plane, then it means that there is no collision. If instead the point is inside the polygon, there is no such line that separates the vertices from the point. So in terms of math, this translates to these equations. So we need to find A and B, where A is a 2D vector and B is a scalar, such that the point P is on one side of this line. So if we compute this linear expression, we get a non-negative value. Whereas the vertices are all on the other side. So if we compute the linear expression for the vertices, then we get negative values. And since this is a line, we can add the constraint that the norm of the vector A should be unit. Yeah.
Aren't these the same problem of the option one? I mean, if such values exist, so if they do not exist, is there a problem?
This is different because this is exactly the opposite of option one. So if there is no collision, then a solution exists. Whereas before it was if there is collision, then a solution exists. And since we want to find collision-free trajectories, this is a much better option than the one we had before. If we wanted to find like in collision trajectories, then we should use the other one.
But if I collide, don't I make a crash of the solver?
If you collide, then the problem is unfeasible. Well, that's kind of what you want when you do collision avoidance. That was the case even before with the circle. If there was collision, then it meant that the inequality constraints representing the collision between the obstacle and the robot did not admit a solution, it was unfeasible. So this is exactly the same situation we were in before. So this is usable to certify collision because if the solver can find a solution to this problem, then it means the robot is not colliding with the obstacle. So to get a bit familiar with this, we can first implement simply the collision check. So I defined this function called check collision, which takes as input the position of the point, so the robot, px, py, and a list of vertices, v. And then what I do is that I create an optimization problem as usual using the class opti. I define my variables of the problem, which are the vector a and the scalar b. I define my inequality constraints. So I want A transpose P plus B to be greater than or equal to 0. And for each vertex in the given list, I want A transpose V plus B to be smaller than 0. So that's exactly the equations, the inequalities I had defined before. And then I also add the constraint that A should have unit norm. I create the solver. I try to find a solution. I try. So if a solution is found, then I say that collision is equal to false because there is no collision. Otherwise, the solver is going to return to raise an exception, which is going to jump, make the code jump here to the except block. And at this point, I can set the collision flag to true because there was no solution, so we must be in collision. I can execute this code. This is just a function which is calling the function defined above and is doing plots to visualize what's going on. Here I'm defining the list of vertices. So it's going to be a polygon with 5 vertices. And this is the result. You can see the polygon in blue, and you can see the points for which we are checking collision here in red. And as you can see in the legend, at this point, the algorithm finds that there is collision. And you can use these sliders to move the point. And as soon as you move it outside, you can see it changes color, it becomes blue, and the legend says point not in collision. And you can also see here the line that is found by the solver. So the separating line, you can see it's a line that separates the point from the polygon. And I can move it, I can move the point wherever I want. As long as it remains blue, it's not in collision. And when it becomes red, it means there is collision. No collision, collision, and then I can go to the other side. I can check it works everywhere. And it seems it does. And this can be generalized very easily also to 3D. You just switch to the vertices being 3D points, and the vector A becomes a 3-dimensional vector. But apart from this small adaptation, the idea is exactly the same. And it's quite powerful because it can work with any convex polygon. So you're not restricted to only like rectangles or trapezoid, whatever, or regular polygons. They can be irregular. I mean, this one is irregular. If you look carefully at it, you can see that this side is not the same as this side. So it's all irregular. And it works just fine. So with this, you can approximate many shapes, even if they're not polygonal. You just take a polygonal approximation and you're done. So this is much more generic than the circular obstacles that we dealt with last time. So now we can try to take this and embed it inside the trajectory optimization problem to do trajectory optimization with polygonal collision avoidance. To do that, we need to extend a little bit what we did, because so far we only checked collision between a point and a polygon. But the robot is not a point. We said that the robot is a circle, which is a quite common shape for wheeled robots. So now we need to check collision between a polygon and a circle or a sphere if you were in 3D. We just need to extend a little bit the formulation. So now instead of checking that the point which represents the center of the robot gives a value which is non-negative when computing the linear form A transpose P plus B, we're going to check that it gives a value which is greater than the ray of the robot. So the only difference with respect to before is that here, instead of 0, we have r, which is the length of the ray of the robot. So basically, it is exactly the same as before in terms of math and complexity. So now we can formulate our trajectory optimization problem. As usual, we start by defining all the hyperparameters. We have a desired state that we want to reach. We have a penalty on the control inputs. We have an initial state, which is zeros. We have bounds on the control inputs. The time step is 0.1 seconds, and we have 25 time steps in our trajectory. Here we create the problem. So the optimization problem that we create is exactly the same we had before. So we use the same function create base problem. And then we simply add the collision avoidance constraints using this for loop here. So let's take a look at what this for loop does. So we iterate over the horizon. So for k ranging from 1 until n, we don't have collision avoidance constraint for the first time step because the initial state is fixed. So it's useless to have constraints on the initial state. We create the new variables, a and b. So we're going to have a value of a and a value of b for each time step in the horizon, because it's not going to be the same a and b over the whole trajectory. We're going to have a different separating line for each time step because the robot moves. So we need to recompute it at every time step. We say that the norm of a should be equal to 1. Actually, this is the square of the norm, but well, if the norm is 1, even the square of the norm is 1, and it's better to avoid square roots in the constraints if possible, so we don't apply the square root, we take the squared norm. And then we say that A transpose times the position of the robot at time step k plus b should be greater than or equal to the ray of the robot. And then for every vertex defining the obstacle, we say that A transpose times v plus b should be smaller than 0. And that's it. That's the only thing we had to add to include collision avoidance constraints. Then the rest of the function is just retrieving the solution and plotting stuff. So not super interesting. Now we define the vertices for the obstacle. And now here we call the function. And we have 2 sliders for moving the obstacle around. So this black polygon here is the obstacle. You can see it has 5 vertices and it is not regular. And I can move it around. Here it's interesting because when I move from this position to this position, even though it seems to me that the previous trajectory would be fine, but the solver completely changes the trajectory. It finds a new one, which is not ideal because it doesn't reach the target. So this is probably just a locally optimal trajectory, which is not globally optimal. And you can see that even here we have the problem of collisions in between time steps. So the position of the robot at discrete time steps is collision free, but if we interpolate in our heads what happens in between time steps, we can clearly see there is collision there. But we already discussed this for circular obstacles, so the same reasoning applies. And you can see as you move the obstacle, of course, if you put the obstacle on top of the target, the robot cannot reach the target. I think that's kind of obvious. Even there, we have probably a local minimum because the robot doesn't reach the target. I would guess there is a way to reach the target from there, even if the obstacle is there. but the solver gets stuck in this locally optimal solution. So we are also seeing the limitations of trajectory optimization. It's very fast. It's quite easy to use with the tools we have available. But the limitation is that sometimes the solver is going to give you a trajectory that looks like that, which is locally optimal. So it's not ideal. What could you do if that happens too often? Simple strategy you could implement to overcome this limitation? Yeah, you could increase the horizon. Maybe that helps. It maybe doesn't. It's not certain, and it comes also with an increased computational cost. There is something else that you can do without really changing the problem.
Creating a two-step solution when first we force the robot to go in an intermediate point, and then it can reach the object, and we choose the intermediate point in such a way that we avoid these weird solutions.
Yeah, that could be an option. I didn't think of that. I was thinking of something else, but yeah, that goes a bit in the direction of like integrating this with trajectory planning, with motion planning. Like if you know techniques like RRT or PRM, so sampling based motion planning, that's a bit of what they do basically. But instead of letting you choose the intermediate points, they choose it basically automatically by random sampling and some optimization over that. There is something else that we can also do, which we discussed last time.
I would put like padding area around the obstacle to avoid a bigger obstacle, but my real one is small.
Yeah, you could change the obstacle shape, but without changing the problem. It's something that we also discussed last time.
Regularization.
Yeah, but that's changing the problem.
Change a little the initial computation.
The initial guess. Yeah, that's what we saw last time. If you change the initial guess you provide to the solver, which at this point we are not providing any, but if you change the initial guess, then you may find a different solution. So maybe you can provide the solver with two initial guesses. Maybe one is reaching like this, the other one is reaching the target like that, and you can optimize both of them in parallel or sequentially, depending on your hardware. And then you can take the best solution out of those two. How do you detect which one is best?
Yeah. I mean, if you reach a local optimum.
Yeah, you can look at the error at the end, the final position. You can check if it's which one gives you a final robot position that is closer to the target. And if that doesn't work, then I would switch to what you suggested. So like providing waypoints that the robot has to reach before reaching the target, which is a bit more complicated, but more powerful.
How should I generate the class project?
That's just up to you. So it depends how much insights you have on the solution. So you should give the solver an initial guess which is as close as possible to the solution. Of course, you don't know the solution, otherwise you wouldn't need a solver. But maybe you have a rough idea of where the robot should go, like whether it should go on the right or on the left. of the obstacle, and you can just give a rough path, which can violate the dynamics of the system. It doesn't matter. It's just guiding the solver to say, hey, search in this region of the trajectory space. So it depends how good you are and how many insights you have and how much effort you want to put into finding an initial guess which is good. And the initial guess is very important in general. So it can change a lot the quality of the solution. Like in this case, we can see that the problem is that the solver decides that the best thing is to move forward until this point and then to proceed moving backward. And it's almost impossible to reach this configuration if you start moving backward from this state here. Because the robot needs to end with this orientation on pointing on the left, and that's basically impossible to reach. So I would say that here we should provide an initial guess which makes the robot move forward and then turn left so that it reaches the final state from the right rather than from the left.
What if in this case I will increase the
Horizon?
execution time?
The execution time, do you mean the horizon?
Yeah.
It could work. I don't know. We can try. So remember 1.2, 1.6 was the obstacle configuration. We can just go backward. I don't know, we can take 35 steps instead of 25. So it was 1.2, 1.6. Yeah, in this case, that works. With a longer horizon, it finds a solution. I think it was possible to find a solution even with a shorter horizon. It was just a matter of initial guess. So I don't think the problem was unfeasible. Because the target is not very far compared to the velocity. So we checked that if you move the target to 4,4, then it's too far to be reached. But here the target is at 2,2. So I think there is enough time for the robot to reach it even with the obstacle in that position. It's just a matter of providing the good initial guess, which is annoying because it takes a bit of work for you, but it may be worth it depending on the application. Okay, so let's summarize everything we have seen. We have seen that we can quickly optimize trajectories to make the robots reach a target while avoiding an obstacle. And by quickly here, I mean really quickly. Because remember, every time I was changing the value in the slider, a new optimization problem was solved and we barely noticed the delay. So it was well below 1 second. I mean, we didn't print the computation time, but I'm sure it was below 1 second. And I'm just running it on my MacBook. I'm not using a super powerful workstation. Just using the one core of my CPU, that's it. And it's all Python. I mean, underneath is not Python. Underneath the solver is in C++. But the code that I had to write to make this happen is all Python, so it's very easy. We could consider multiple obstacles at once, even though we didn't do it. I did it in a different script. It works just the same. So you could have multiple polygonal obstacles, circular obstacles. You just add the pairs of variables a and b for each polygonal obstacles. So you are increasing the size of the decision variable, but it still works, just a bit slower. And yeah, we have seen circular polygonal shapes. There are other shapes that can be considered inside trajectory optimization problem. Capsules, for instance, are a big one. So a capsule would be in 2D, it would be a rectangle with two half circles at the end. That's called a capsule. And that is very practical and very often used in trajectory optimization because it's easy to check collision between capsules. But I think that already with circles and polygons, you can go a long way. We have also seen that there are some limitations to this approach. One is that we can only ensure constraint satisfaction at discrete time steps. So we might have collision in between time steps, but there are approaches that can be implemented to either mitigate or even completely solve this issue, like adding extra constraints or decreasing the time step or checking collision with the convex hull of the robot shape at consecutive time steps. And another issue that we encounter sometimes is the one of local minima. And there we saw that we have a tool at our disposal for solving this, which is providing the solver with an initial guess. Takes a bit of creativity and trial and error. There's no guarantee here, but in practice, that's very often solving the issue. Let's briefly discuss a couple of extensions. So one thing that you maybe don't like about the trajectories that we have been computing is that they have a tendency of going very close to the obstacles, right? We have seen, and that actually is also what creates the problem of having collisions in between time steps, because at the discrete time steps, the robot tends to really go super close to the obstacle because that's what optimality requires it to do, since we want to minimize the control efforts, because we have this term in the cost function. Then typically the optimal trajectory is the one that really touches the obstacle when reaching the target. That's not ideal in terms of robustness, because even if we extended it to have really no collision in continuous time, then if you go and execute that trajectory on a real robot, you're going to have some noise, some small deviations from the reference trajectory which we compute. And what might happen is that the robot hits the obstacle because we have no safety margin. So one thing one could do is, well, I can just make my obstacles a bit bigger or make my robots a bit bigger, works the same, so that I have a safety margin. But then the problem is, how do you decide how much safety margin you want? Because if the safety margin is not enough, again, you might have collisions on the robot. And if you make the safety margin too large, then that also might be a problem, because you may have a problem which becomes unfeasible. Imagine the robot has to go through a door, and the door is slightly bigger than the robot. If you make the safety margin too large, then the robot doesn't fit anymore and it cannot go through the door. So ideally, you would like a safety margin which is automatically computed by the solver. And you can do that. You just introduce an extra variable inside your problem, S, which you constrain to be non-negative. And that variable represents the safety margin. You put a term in the cost function to maximize the safety margin. So you put it with a minus in front so that you minimize minus the safety margin, so you maximize it. And you add the safety margin inside your collision avoidance constraints. So your constraints are of the form A transpose P plus B greater than or equal to R. You add the safety margin to this constraint. And so the robot tries to find a trajectory that not only satisfies the constraints, but satisfies them with a safety margin which is as large as possible. So if you implement that, and I suggest you to try, it's fun, and it gives you some practice, you will see that by tuning the weight of this term in the cost function, you can basically find a compromise between optimality, so reaching the target in the most efficient way, and robustness, so leaving a safety margin between the robot and the obstacles. So you get like a robust trajectory optimization in this way. Another possible extension is if you wanted smoother trajectories. So at the moment, we are modeling the robot at the velocity level. So the control inputs of the robot are the velocities, which means that the trajectory might be not very smooth. So the robot could be moving at maximum velocity, so 2 meters per second at one time step. And at the next time step, it could be just still. So it means it has to decelerate very quickly. So of course, as long as you're using simulations, that's not an issue. But when you go on a real system, such behaviors typically don't go very well with the hardware. So you might need to have more smooth trajectories. Well, one way to do that is to change the dynamic order of the system. For instance, you could say that your control inputs become now the accelerations, and your state contains both positions and velocities. And if you do that, then of course you're going to get smoother trajectories, because the velocities can no longer change abruptly, because you're going to have inequalities or bounds on your acceleration, so the velocities can only change with a certain rate of change, which is the one you specify as acceleration limit. And you can extend this even to higher order. You could have the control inputs, which are the derivative of the acceleration, which is the jerk. And then your state includes positions, velocities, and accelerations. And then you get even smoother trajectories, because then you're going to have also continuous accelerations. So you can push that to any orders that you want. So for moving on the hardware, that's actually very useful. So you can see that overall, it's a very flexible tool, as the one you have in your hands, and you can adapt it to meet all your needs depending on the application. It just takes a bit of experience and creativity. So that's it for this notebook. Any question? Okay, it's a bit early, but it's a very good moment to take a break. So I suggest we take it. After the break, we're going to continue with MPC. So if you want to start to open the file, you can find it here. It's inside optimal control, Casati-Adam X2, so exercise 2. This is the next file we're going to play with, and we're going to implement MPC for a robot manipulator in this file. So let's take 10 minutes. I'll see you back here at 27. Okay. So you can open this file if you haven't already. It's in optimal control / Casati-Adam / x2.py. The script should feel very similar to the ones we have already seen when implementing shooting and collocation for a robot manipulator. So last time we were doing this in a Python notebook. This time we have a normal Python script, but apart from that, they are very, very similar. So I'm going to focus mainly on the differences with respect to the formulations we have already seen. The formulation that's going to be used here is collocation, because we have seen that actually for this solver, at least, collocation leads to much faster computations than shooting. You can see here some flags that are interesting, like this one, do warm start. This is related to the initialization of the solver, because we said that the main thing that we need to add when we do MPC is providing an initial guess to the solver, and we're going to use the trajectory computed at the previous control loop as an initial guess for the next optimization. We have specified the solver tolerance, 10 to the minus 4. That's a very rough tolerance we're asking for, because since we're doing MPC, we don't care about having accurate solutions. We care about having fast solution. And even more important than that, we are specifying a maximum number of iterations for the solver. So even if the tolerance is not met, after 3 iterations, we stop the solver, no matter what. Because we have real-time constraints, we cannot allow the solver to compute for longer than a certain computation time. So if you want to ensure that the solver finishes its job in a given time window, providing a maximum number of iterations is actually the best way to achieve that. It's better than working with the convergence threshold, because you don't know how long it's going to take to reach that convergence threshold, but you can know quite accurately how long it's going to take to do 3 iterations, because each iteration roughly always takes the same amount of time. And then you can choose which simulator you want to use. And here I provided 3 options, which are ideal, Pinocchio, and Mujoko. Ideal, it means that actually there is no simulation, and we just take the predicted next state as the real next state. So that's the ideal scenario in which the prediction of the solver is really matching what happens in reality. Of course, that's not very realistic. Pinocchio is a bit more realistic, because what's going to do is that it's going to take the control inputs computed by the solver for the first time step, so U0, and it's going to use that U0 for simulating the system forward in time. And if the simulation model is a bit different from the model used in the solver, then this is not going to lead to the same state that is computed by the trajectory optimization solver. So there's going to be a bit of a mismatch between the state that we reach and the state that we had predicted to reach. And in this case, actually, the 2 models are going to be the same, and the mismatch is only due to the fact that the solver is not exactly satisfying the dynamics constraint, because we are giving it only 3 iterations when solving the problem. If we were giving the solver more iterations, then actually Pinocchio and ideal would be the same. But since we are not, then they're different. And then there is a third option, which I don't think you can use because you don't have this option installed in your machine, which is Mujoko. Mujoko is a simulator which you could try installing, but last year everyone who tried reported some issues, so this year I didn't even tell you to install it. Anyway, it's not needed. You just are going to work with one of the other 2 options. But it is, if you want a real simulator in the loop, then this is implemented with Mujoko. I don't know if you're even going to use this today. Then here I'm just scaling the position and velocity bounds by some factor to make the problem a bit more interesting. I'm setting up the time step to 2 milliseconds. Then this is actually the simulation time step, which is not the MPC time step. So I'm simulating with a time step which is smaller to have a more accurate simulation than I have instead in the MPC. And I'm simulating for 100 time steps in total. Initial state is just all zeros. The MPC time step is 10 milliseconds, and I'm using a quite short horizon, 6, which is needed to have fast computation. And here I'm setting the desired joint angles for the final state of the robot to be actually very close to the one of the joint limits for joint 1. So the desired final configuration is actually equal to the initial one, except for joint 1, whose desired angle is very close to Q min. Because I'm taking Q min and I'm added to it 1% of the range of that joint. So we are very close to Q min, but not exactly at Q min. The reason I'm doing that is that this is going to make it hard for the controller to avoid hitting on the Q min limit for that joint, since I'm trying to reach a target which is very close to the bounds of that joint. Here I'm specifying the weight of the cost function. I have a cost term on position, one on velocity, one on the acceleration, and one on the final velocity. And these are the weights that I'm using. Then here I'm creating the simulator, which could be either a Mujoko simulator or a robot simulator, which is the one we have been using so far. And here I start defining the optimization problem in Casati, which is going to be basically exactly the same as we saw last time, with one difference, is that this time, since we need to solve the same problem inside the loop for several times in a row, I'm going to define a parametric problem. So what's a parametric problem? It's a problem with parameters, which means that there are certain parts of the problem for which I can specify a different value every time I try to solve the problem. This is just for avoiding to recreate the problem from scratch every time, which would take a lot of computation time. So I only create it once, but with parameters. And every time that I want to solve the problem, I just set the values of the parameter to a different value and then recall the solve method. And the parameters here are the initial state, because that's actually the only difference when I do MPC. The problem is exactly the same. The only thing that changes is the initial state. And I also set as parameter the desired joint angles, even though in this specific script, I'm not changing it. But in many applications, you want to track a moving target. And so the desired configuration changes as you keep calling the method. So you can create parameters using this method, opti.parameter. It's like creating a variable, basically, but it has a different meaning. Apart from that, the specification of the problem is exactly the same. So I'm not going to go over this. We can just take a quick look at the cost function. Cost function, we have a penalty, a running cost on the tracking error with respect to the desired joint angles. We have a penalty on the joint velocities and a penalty on the joint accelerations. Remember that U are the joint accelerations. We have the dynamics. We have the joint torque bounds. And we have a final cost on the joint velocities. That's it. Then we create a solver. We specify the tolerance that we want the solver to reach, which is 10 to the minus 4. And for the first time that we call the solver, we set actually the maximum number of iterations to be very large, because the first time we solve the problem, we don't need to be fast, because the robot hasn't started to move yet. So we can take our time. It's only when we start the control loop, then we start moving the robot, that we need to solve the problem fast. So the first problem, you solve it until convergence, so that at least you start with a good solution. So here, maximum number of iterations is 1000. And here we need to set the value for the parameters, so qdes and xinit. We set it using this method set value. and then we solve the problem for the first time. But after solving it to convergence, we set the maximum number of iterations to be 3. And we recreate the solver, because every time you change a parameter of the solver, you need to recreate the solver. So now, every time you're going to call the solve method, the solver is just going to do 3 iterations, and then it's going to stop.
So in the first, I do 1000, and in the other 3.
Yeah, exactly. And here we start the MPC loop. So we're going to iterate for nsim iterations. And here we need to implement the code for the MPC. So this is the part where we need to write some code. And after we have implemented our code here, the rest of the loop is simply computing the joint torques using the solution that is computed by the MPC. Because the MPC doesn't directly compute the joint torques, it computes joint positions, velocities, and accelerations. So the joint torques needs to be computed afterwards. And then it's depending on which solver we are using, it's simulating the system with a given simulator. And it's displaying the motion of the robot in the viewer. And these final 4 lines are just checking whether the joint position bounds are satisfied or not, because that's going to be critical in this setting. So in case we are violating the joint position bounds, we're going to see error messages in the terminal. So what I would like you to do now is to take some time to implement the MPC control loop here. So let me give you a few tips. Make sure to warm start the solver. Use opti.setInitial to specify initial guesses for the decision variables. And another thing you need to do is specify the initial state parameter, which is param x init, using opti.setValue as above. So it's basically this line here that you also need inside the control loop. And another piece of advice is use a try except block to call opti.solve, because it may return an error. So when you call the solver, if the solver doesn't find a solution for some reason, it's going to raise an exception, but you don't want to stop the control loop, you want to keep going. And so you're going to call it inside the try except block, which is going to be something like that: try code except code. So this is where you're going to call the solve method. And here is where you're going to deal with the exception, but actually you're going to do nothing. You're just going to ignore that there was an exception. And I think that's it. So you can try to implement this, and then, well, we have still 45 minutes. Maybe I give you half an hour to work on that. And then the last 15 minutes, I show you the solution. And of course, if you have any question, I'm here. Let me start maybe just to implement a partial solution so that who is completely lost gets back on track. So the very basic thing that we have to do is to solve the problem, which is sol equal opti.solve. This is what we need for solving the problem. Here, in case there is an exception, we can just say there was an error while solving the problem. Just to start very, very simply. And the other thing that is really important is to set the initial state, because if we just solve the problem, then it's going to work always with the same initial state, which is the one we have set here, which is meaningless. We need to solve the problem from the new initial state. So we need to just copy this line. So this is a very basic thing that we have to do to have something that works. We haven't done the warm start yet, so it's going to be slow because every time it's going to recompute a solution from scratch, but it should work. Of course, if we want to make this really work, we need to give the solver more than 3 iterations. So maybe I can just change that to 100 temporarily just to make a test and see what that gives me. Python x2.py, let's see. Okay. I have a robot that moved. And here it printed lower position limit violated on joint 1 at a certain point in time. It doesn't print at which point in time that happened, but maybe we can just print the time here. Time step. And run again. Okay, so there were these 3 time steps where we had violations of the joint position limits. But apart from that, the behavior is okay. Now, the simulation that we are using, however, is the ideal. So we are assuming that we reach the state that we predicted. If we wanted a more realistic simulation, we should switch to Pinocchio. Let's see how that changes. Well, we violated the position limits more than before. And there was a moment when there was an error while solving the problem. Which didn't happen before when using the ideal simulation. Actually, here, when there is an error, if you don't do anything, then what's going to happen is that at the moment we are just reapplying the solution computed as the previous loop, which may be not ideal. I think it's better at that point to use, even if there was an error, to use the solution that was computed at this time. And to do that, we need to do that. I think sol equal opti.debug Let me check. Yeah, is that. And another thing we can try is to take a look at the computation time. Okay, I don't need to use time dot. I just imported clock. So here I can also print computation time and time minus start time. So we can take a look at the computation time. So computation time, first of all, it's not constant. So we start with 62 milliseconds, then it gets a bit slower, around 35, 30, 35. Then again here 65. And then here when we start having trouble, it actually takes more time. Here we got to 150 milliseconds, 114, 120, 114. So this is quite slow. And then it goes back to being around 30 milliseconds. So if we wanted to implement this on a real machine, we should really avoid having these peaks in the computation time. And one way we can try to avoid those peaks is by providing the warm start. So let's try to implement the warm start. Oh, you have a question?
Yes. Which parameter do you change to not have error in solving the problem?
I didn't change anything.
Oh.
I think there is this flag here, error on fail, which I set to false. But that was already predefined in the script, so you should have it as well.
I have problem. I have error from the start of the C loop.
It's very generic description, so I don't know how to help you at this point. Maybe you can take a look at it later. So let me try to do the warm start. So we can use the flag that I've introduced, do warm start, just to be able to disable it if we want at a later stage. So the method that we need to use for warm starting is set initial. So opti.setInitial. And this method takes as inputs the variable that we want to warm start and the value for that variable. So the variables that we want to warm start are, well, the states and the control inputs. So something like xk. What is the value that we want to specify? It's the value computed by the solver at the previous iteration. So how do we recover that? Well, we have an example here. This is how you recover the value computed by the solver. You just do sol.value, and then you specify which variable you want to recover the value of. So this is not going to be xk. because what was xk at the previous iteration is not xk now because the horizon has moved forward. So we have a shift of 1. So what was x1 before now should be x0. Okay, so here we should specify xk plus 1. And we need to do that inside the loop. And we're going to have to do the same for the control inputs. Just need to be careful because the range of the control inputs is not the same as the range for the states. Control inputs stop at n minus 1, while the states stop at n. So here we need to set the range until n minus 1, not until n. And that leaves out the last control inputs and the last state, which are not initialized. Because well, when we shift everything backward, of course, we miss the last one. So if we want also to specify an initial guess for the last state and the last control input, we need to do it outside. And here for the final state, I would say we specify the same initial guess as the one before that. And we do the same for the control inputs. This is rather arbitrary. We could also use other strategies. So we can, first of all, not do the initial guess and just see how it behaves when we set the maximum number of iterations to 3, which we haven't tested yet. We should behave very poorly. And indeed, it does behave very poorly. See, it went all the way to the other side, whereas it should stop in the top configuration. And yeah, there were many errors. So the computation time now is better. You can see it's 12 milliseconds, whereas before it was always around 30 with some peaks. Now it's quite consistently at 13 milliseconds because we have only 3 iterations, so it cannot take too long. But we have lots of errors. Like every time there was an error, you can see. Well, these errors here, I think they are just due to the fact that if the solver reaches the maximum number of iterations, that is an error for the solver. We can check that later by printing the error message of the solver, but it's probably going to be only that. But we can see that the violation of the joint limits now is much more present than it was before. And now we can instead see what is the effect of the warm start. Let me check that the flag is set to true. Yeah, it is set to true. So with the warm start, it's not better. So let's see. Yeah, we still have lots of errors. Computation time is good, of course, because we are limiting the number of iterations, but the warm start alone is not sufficient. This was with Pinocchio. I guess if we switch to ideal, it should work better. Yeah. This is closer to the behavior that we want. So if we switch to ideal, actually, there is no problem. So there is no violation of the joint limits. This print, I think it's misleading. I can remove it because it's going to go here every time just because it reaches the maximum number of iterations before converging. So it's not really a problem. So we can see that actually everything went fine if we switch to the ideal simulation, but the ideal simulation is not realistic. It's just assuming that my prediction is exactly matched by reality. What could be the problem? Well, we don't have really time to discuss it, so I leave that as a question for you. Why could still the solver be failing when using the Pinocchio simulation? So when we use Pinocchio, we have good computation time, but bad behavior of the robot. And this is related to something that we've studied during our lecture on MPC. So I wanted to think about it. And then on Friday, we keep going with this and I give you the solution. But come with an answer. I'll see you on Friday.